Okay, right now we're going to talk about the specific latent heat, and what this is basically the energy that happens within phase changes. Okay, so we're going to define what specific latent heat is, and we're going to solve problems involving specific latent heat. So this is very important for changes of state, so moving from liquid to a solid, or from a solid, from a liquid to a solid, or from a gas to a liquid. Okay, so there's two important definitions we need here. The first type of specific latent heat is specific latent heat of vaporization, and that is the heat required to boil a unit mass of material at its boiling point. So let's say our unit mass is 1 kilogram. How much heat do we need to put in to this material? Let's say it's water. How much heat energy do we need to put into water to boil away 1 kilogram of that water? Okay. And there's a similar definition for the specific latent heat of fusion. So the specific latent heat of fusion is the heat required to melt a unit mass of material at its melting point. And so let's use the example of water again. Let's say we have an ice cube. Let's go bigger than. Let's say we have a block of ice that weighs 1 kilogram. That's our unit mass, is 1 kilogram. How much heat energy do we have to put into that frozen ice block to essentially cause all of that to melt? Okay, so it's basically the heat required to make a phase change, to cause that phase change. Okay, and we can measure this quantitatively using the equation Q equals mL. So Q and M are the typical definition. So Q is heat, and heat is a type of energy, so that's measured in joules. M is just the mass, and the SI unit for mass is kilograms. And L, well, if we rearrange L, that's the heat divided by the mass, okay? And what that is that's the specific latent heat, okay? And we rearrange the equation, so we should be able to tell what the units are. And the units of Q, heat, is energy divided by mass, which is kilograms. So it has units of joules per kilogram. Okay, so let's look at a practical example. So let's say we want to boil some water. Okay, so first we need some water. So throw some water in there. And then what we're going to do is throw some heat energy into that water, and that's going to cause it to basically, eventually, gradually, the temperature of this water is going to get very high and it's going to start to boil. Now, as we looked at in the last video, when it starts to boil, or even not boil, it starts to evaporate. But as the heat energy increases, more and more particles of liquid are going to escape. Okay, and if you look at the definition of specific latent heat of vaporization, it is how much heat is required to melt a unit mass. Okay, so what it is, if we look at this equation, is heat divided by mass. So let's say we have some amount of heat energy for some material. Okay, so let's say we put in 1 kilojoule of heat energy. So that is equivalent to 1,000 joules. And let's say the mass that boils away, so the mass that changes into the change of state, is, we'll keep it relatively simple. So let's say that's 2 kilograms of material. Okay, well, L equals the heat energy divided by the mass, which is 1,000 joules divided by 2 kilograms. So that is a specific latent heat of vaporization of 500 joules per kilogram. And if we put it in proper SI units, joules kilogram to the -1. Okay, so specific latent heat, just as some examples and some theoretical comparisons, the specific latent heat of vaporization of water is 334 kilojoules per kilogram, and this is H2O. whereas the specific latent heat of fusion is 2,260 kilojoules per kilogram. Okay, so if you happen to do any experiments where you boil away water and you see some escape, the mass that escapes, okay, and you find the heat energy, which can come from, for example, power. So power times time gives you the amount of heat energy. Okay, you use this equation right here, and you're able to find the specific latent heats of these properties. Okay, so that's kind of an example of how experimentally you would be able to determine these values. Now, it can get a bit more confusing when we add specific latent heat. So in the next video, I'm going to show you an example of how we can put the two together and look at